If you're over 60 and you have noticed your legs feel heavier, colder, weaker, or tire more quickly than they used to, this is not just a sign of getting older. It's a signal, one that your blood vessels are asking for help. As we age, blood flow to the lower limbs often declines. The arteries stiffen, the inner lining of blood vessels, the endothelium, becomes less responsive, and the tiny capillaries that once delivered oxygen and nutrients efficiently begin to disappear. This reduction in circulation doesn't just affect comfort, it directly impacts muscle strength, balance, nerve health, and even your ability to stay independent. Now, here's the important part. This process is not inevitable. Modern longevity science shows that vascular aging is deeply connected to cellular energy production, inflammation, and nutrient signaling. And one specific vitamin, often misunderstood, sometimes overlooked, plays a surprisingly powerful role in restoring blood flow, particularly in aging legs. This vitamin doesn't work by forcing blood vessels open like a drug. Instead, it helps your cells generate the signals they were designed to produce when they were younger, signals that tell blood vessels to relax, repair, and regenerate. In today's talk, I want to explain why leg circulation declines after 60, how this vitamin supports healthy blood flow at the cellular level, and what the science actually says about using it safely and effectively, not as a miracle cure, but as a tool for healthier aging. Because aging well isn't about fighting your biology, it's about working with it. One of the most persistent myths about aging is that circulation simply slows down as a passive consequence of time, as if blood flow fades the way ink fades on old paper. But biology is rarely that simple, and almost never that helpless. What actually happens in the legs after 60 is not a single failure, but a cascade of small compounding changes at the cellular, vascular, and metabolic levels, and understanding this cascade is the first step toward interrupting it. Let's begin with the blood vessels themselves. Arteries and veins are not inert plumbing, they are living tissues lined with a delicate layer of cells called the endothelium. In youth, this endothelial layer is remarkably responsive. It senses changes in blood flow, oxygen demand, and physical movement, and it responds by releasing signaling molecules, most notably nitric oxide, that tell the vessel to relax, widen, and increase circulation where it's needed. As we age, particularly after 60, this signaling system begins to falter. Endothelial cells become less efficient at producing nitric oxide, not because the body forgets how, but because the cellular machinery that supports this process becomes compromised. Mitochondria, the energy-producing structures inside cells, grow less efficient over time. When endothelial cells lack sufficient energy, they prioritize survival over optimization. Blood vessels still function, but they lose flexibility. They respond more slowly, less completely, and sometimes not at all. This is especially problematic in the legs. Unlike the heart or brain, which receive preferential blood flow even under stress, the lower limbs are physiologically disadvantaged. Blood must travel against gravity, arteries must deliver oxygen over long distances, veins must work harder to return blood to the heart. When vascular function declines, the legs are often the first place where the deficit becomes noticeable. But vascular aging is only part of the story. Another major contributor is the gradual stiffening of arteries, a process driven by changes in the extracellular matrix, the scaffolding that holds tissues together. With age, elastin fibers that give arteries their youthful stretch begin to fragment, while collagen, which is stiffer and less forgiving, accumulates. The result is arteries that are less able to expand with each heartbeat. This reduces pulse pressure and limits the surge of blood that normally reaches working muscles during movement. At the same time, low-grade chronic inflammation, sometimes called inflammaging, quietly accelerates vascular decline. Unlike acute inflammation, which is short-lived and protective, chronic inflammation subtly damages tissues over decades. In blood vessels, it interferes with endothelial signaling, increases oxidative stress, and promotes the buildup of plaques and calcification. None of this happens overnight. It unfolds slowly, often without symptoms, until circulation is compromised enough to affect daily life. Another often overlooked factor is capillary density. In younger individuals, skeletal muscle is richly supplied with tiny capillaries that deliver oxygen directly to muscle fibers. These capillaries are not fixed structures. They are dynamic, responding to physical activity, metabolic demand, and growth signals. Unfortunately, with age and especially with reduced movement, capillary networks begin to regress. Fewer capillaries mean less surface area for oxygen exchange, even if larger arteries remain relatively open. This helps explain why some people over 60 can have normal cardiovascular test results, yet still experience heavy, tired, or weak legs. Large vessels may appear adequate, but microcirculation, the true workhorse of tissue health, has quietly deteriorated.
Muscle itself also plays a role in this process. Healthy muscle contractions act as a pump, helping propel blood back toward the heart. As muscle mass and strength decline with age, this pumping action weakens. Blood pools more easily in the lower extremities, increasing pressure in veins and reducing the efficiency of arterial inflow. Over time, this creates a feedback loop. Poor circulation accelerates muscle loss, and muscle loss further impairs circulation. Metabolic health adds another layer of complexity. Insulin resistance, which becomes more common with age, directly impairs endothelial function. Elevated blood glucose and insulin levels increase oxidative stress and reduce nitric oxide availability. Even in people who have never been diagnosed with diabetes, subtle metabolic dysfunction can significantly affect blood flow, particularly in peripheral tissues like the legs. And then there's the role of cellular communication. Aging cells don't just lose function, they lose coordination. Signaling pathways that once synchronized vascular repair, energy production, and inflammation control begin to drift out of alignment. This is one reason why aging feels systemic rather than localized. When circulation declines in the legs, it's often a reflection of broader communication breakdowns throughout the body. Importantly, none of these processes are binary. Blood flow doesn't suddenly switch off at 60. It diminishes gradually, often unevenly, influenced by genetics, lifestyle, physical activity, nutrition, sleep, and stress. Two people of the same age can have dramatically different vascular health profiles, depending on how these variables interact over time. This is also why aging research has shifted away from treating symptoms in isolation and toward understanding upstream causes. Poor leg circulation is not just a plumbing issue. It's a sign that energy production, inflammation control, and cellular signaling are no longer operating in youthful harmony. From a longevity perspective, this matters enormously. Reduced blood flow to the legs doesn't just affect walking endurance. It affects balance, reaction time, nerve health, and recovery from injury. It increases the risk of falls. It limits physical activity, which in turn accelerates metabolic decline and muscle loss. What begins as a vascular issue can ripple outward into nearly every aspect of health span.
Yet, and this is the critical point, vascular aging is remarkably responsive to intervention. Endothelial cells retain the ability to recover function when given the right signals. Capillary networks can regrow. Nitric oxide production can be restored. Arterial stiffness can be slowed and in some cases partially reversed. The biology that governs blood flow is adaptive, even later in life. Understanding why blood flow to the legs declines after 60 is not about resignation, it's about precision. When we identify the specific mechanisms involved, mitochondrial decline, endothelial dysfunction, inflammation, capillary loss, we gain leverage. We move from vague advice like stay active to targeted strategies that support the systems most responsible for keeping blood moving efficiently. Aging at its core is a loss of information, a gradual failure of cells to remember how to cooperate as they once did. Circulation is one of the clearest expressions of that cooperation. When it falters, it's not a verdict, it's a message. And biology, when understood, often gives us more room to respond than we've been led to believe. When we talk about improving blood flow, especially in aging legs, the conversation is often dominated by medications that force blood vessels to dilate, or by exercise prescriptions that, while effective, don't fully explain why they work. But biology is more elegant than brute force. The most powerful interventions tend to restore the body's own signaling systems rather than override them. This is where one particular vitamin becomes especially interesting, not because it acts like a drug, but because it helps aging cells remember how to communicate. At the center of healthy blood flow is nitric oxide. This small, short-lived molecule plays an outsized role in vascular health. It tells blood vessels when to relax, when to widen, and how to respond to increased demand from muscles. In younger individuals, nitric oxide production is robust and tightly regulated. Endothelial cells sense movement, shear stress from flowing blood, and metabolic need, then respond almost instantly by releasing nitric oxide. The result is smooth, adaptable circulation. With age, this process becomes impaired. Nitric oxide production declines not simply because the enzyme responsible, endothelial nitric oxide synthase, stops working, but because the cellular environment it depends on becomes hostile. Oxidative stress increases, mitochondrial efficiency decreases, and inflammatory signals interfere with normal enzyme function. Nitric oxide, when it is produced, is more quickly neutralized by free radicals before it can exert its effects. The vitamin we're focusing on acts upstream of these failures. Rather than forcing vasodilation, it supports the cellular conditions that allow nitric oxide signaling to occur naturally and sustainably. This distinction is critical. Forced dilation can temporarily improve blood flow, but it doesn't address the underlying age-related decline in vascular intelligence. Supporting signaling, on the other hand, helps restore adaptability, the hallmark of youthful physiology. One of the key ways this vitamin works is by improving endothelial cell metabolism. Endothelial cells are often overlooked in discussions of energy production, yet they are metabolically active and highly sensitive to energy deficits. When mitochondria inside these cells struggle, nitric oxide production becomes erratic.
By supporting mitochondrial efficiency and reducing oxidative stress, this vitamin indirectly enhances nitric oxide availability. The cell doesn't just make more nitric oxide, it preserves it long enough for it to do its job. There is also an important interaction with inflammation. Chronic low-grade inflammation disrupts vascular signaling by activating pathways that oppose nitric oxide's effects. This vitamin helps shift that balance. It modulates inflammatory signaling at the cellular level, reducing the background noise that prevents blood vessels from responding appropriately. Think of it not as turning the volume up on nitric oxide, but as quieting the interference that drowns it out. What makes this particularly relevant for the legs is the unique challenge of peripheral circulation. Leg muscles require large, rapid increases in blood flow during movement. They rely heavily on precise timing between demand and delivery. Even small impairments in nitric oxide signaling can translate into noticeable fatigue, heaviness, or weakness. Supporting this signaling pathway therefore has outsized benefits in the lower extremities. From a longevity perspective, this vitamin is also intriguing because it intersects with pathways involved in cellular stress resistance. Aging cells are constantly deciding how to allocate limited resources. When signaling pathways are distorted, cells default to conservation rather than performance. By improving metabolic signaling and redox balance, this vitamin nudges cells back toward a more youthful decision-making process, one that favors repair, responsiveness, and adaptability. It's also worth addressing a common misconception that vitamins work simply by correcting deficiencies. In younger individuals, that may often be the case, but in aging, the story is more nuanced. Many older adults have normal blood levels of various nutrients, yet still experience functional deficits. This is because aging alters how cells use nutrients, not just how much of them are available. The vitamin in question appears to enhance utilization, not merely supply. It helps cells extract more functional value from the nutrients already present.
Another important aspect is timing and context. This vitamin doesn't operate in isolation. Its effects on nitric oxide signaling are amplified by movement. Physical activity increases shear stress on blood vessels, which is one of the strongest natural triggers for nitric oxide release. When the signaling machinery is supported, even modest activity, walking, standing, light resistance, can produce disproportionately large improvements in blood flow. This synergy is essential. Supplements that work with behavior tend to produce more durable results than those that attempt to replace it. Safety and sustainability also matter. Because this vitamin works through endogenous pathways, its effects are generally gradual rather than dramatic. This may seem less appealing in a culture that favors quick fixes, but from a biological standpoint, it's a strength. Gradual improvements are more likely to be maintained and less likely to provoke counter-regulatory responses. Blood vessels adapt over weeks and months, not hours. In research settings, improvements in vascular function associated with this vitamin are often measured not just by blood flow, but by markers of endothelial responsiveness, how well vessels react to stimuli. This distinction is crucial. A vessel that can respond appropriately is healthier than one that is merely open. Responsiveness reflects intact signaling, energy availability, and structural integrity. There is also emerging interest in how this vitamin interacts with age-related changes in gene expression. As we age, certain genes involved in vascular repair and antioxidant defense become less active. While no vitamin can turn back the clock, supporting the cellular environment can influence which genes are prioritized. In animal and early human studies, improved nutrient signaling has been associated with gene expression patterns more typical of younger tissue. This is not rejuvenation in the science fiction sense, but it is a meaningful shift in trajectory. Perhaps the most important point is this: improving blood flow through signaling support respects the body's innate intelligence rather than dictating outcomes. It restores capacity. It allows blood vessels to do what they evolved to do, respond dynamically to changing needs. For the aging legs, this can mean the difference between movement feeling like a burden and movement feeling natural. In the broader context of healthy aging, circulation is a linchpin. It connects metabolic health, muscle preservation, nerve function, and physical independence. When we support the molecular language that governs blood flow, particularly nitric oxide signaling, we are not just improving circulation, we are reinforcing the communication network that keeps tissues alive, responsive, and resilient. Aging does not erase this network, it distorts it, and distortion, unlike destruction, can often be corrected if we know where to intervene. When people think about circulation, they often imagine it as a delivery system. Blood goes in, blood comes out, job done. But in biological terms, circulation is far more than transport. It is communication. Blood flow carries oxygen and nutrients, yes, but it also carries signals that tell tissues how to behave, when to repair, and whether to grow stronger or quietly deteriorate. Nowhere is this more evident than in the legs, where improved blood flow can mean the difference between gradual decline and functional resilience after 60. Let's start with muscle.
Skeletal muscle is one of the most metabolically demanding tissues in the body. Even at rest, muscle cells require a steady supply of oxygen and nutrients to maintain protein turnover, mitochondrial function, and cellular housekeeping processes like autophagy. With age, muscle loss, what we call sarcopenia, is often blamed solely on declining hormones or reduced activity, but circulation plays a foundational role. When blood flow is compromised, muscle cells are forced into an energy-conserving mode. Protein synthesis slows, repair processes are delayed. Over time, muscle fibers shrink not because they are unused, but because they are undernourished. Improved blood flow reverses this trajectory at multiple levels. Increased oxygen delivery enhances mitochondrial efficiency, allowing muscle cells to generate energy more effectively. Better nutrient delivery supports amino acid uptake and protein synthesis. Importantly, improved circulation also facilitates waste removal, clearing lactate, carbon dioxide, and inflammatory byproducts that accumulate during activity. This creates a cellular environment where muscle can respond to exercise signals rather than resist them. This is why individuals with better leg circulation often experience faster gains from the same amount of physical activity. The exercise stimulus is identical, but the biological response is not. Blood flow determines whether movement becomes a signal for adaptation or simply another stressor to endure. Nerves are equally dependent on circulation, though their needs are often overlooked. Peripheral nerves in the legs are long, delicate structures that rely on a dense network of tiny blood vessels for nourishment. As circulation declines, nerves are among the first tissues to suffer. Reduced blood flow impairs the delivery of glucose and oxygen to nerve cells and disrupts the function of Schwann cells, which insulate nerve fibers and maintain signal speed. The result can be subtle at first: occasional tingling, reduced temperature sensitivity, delayed reflexes. Over time, these changes can progress to numbness, weakness, or poor coordination. These are not merely sensory inconveniences. They directly affect how the brain perceives the position of the body in space, a sense known as proprioception. Improved blood flow helps preserve nerve health by restoring the metabolic support nerves require. Enhanced circulation improves myelin maintenance, supports neurotransmitter balance, and reduces local inflammation around nerve fibers. When nerve signaling is clearer and faster, the brain receives more accurate information about foot placement, joint position, and muscle tension. This has profound implications for balance and stability. Balance itself is not a single function. It is an emergent property of multiple systems working in synchrony: muscles generating force, nerves transmitting signals, and the brain integrates sensory input in real time. Blood flow is the silent enabler of all three. When circulation to the legs improves, muscles respond more quickly, nerves transmit signals more reliably, and the entire feedback loop tightens. This is why research and studies when circulation improvement can reduce fall risk even in the absence of dramatic strength gains. Reaction time improves, postural adjustments become more precise, small stumbles are corrected automatically rather than escalating into dangerous falls. From a longevity perspective, this matters enormously. Falls are one of the leading causes of loss of independence after 60, and circulation is a modifiable contributor. There is also an important connection between blood flow and muscle quality, not just muscle size. Aging muscles often undergo fatty infiltration, where fat replaces contractile tissue. Poor circulation accelerates this process by limiting oxygen availability and promoting insulin resistance within muscle cells. Improved blood flow enhances insulin sensitivity, encouraging muscles to use glucose efficiently rather than store energy as fat. This preserves strength per unit of muscle mass, which is far more predictive of functional ability than size alone. Another layer to consider is recovery. Aging bodies recover more slowly from physical stress, and circulation is a primary reason why. After exercise or even prolonged standing, muscles accumulate metabolic waste and experience microdamage that must be cleared and repaired. When blood flow is robust, this recovery process happens efficiently. When circulation is compromised, recovery stalls, leading to prolonged soreness, stiffness, and reduced willingness to stay active. Improved circulation shortens recovery windows, making it easier to maintain consistent physical activity, which in turn further supports vascular health. This creates a virtuous cycle rather than the vicious cycle of declining circulation, leading to reduced activity, leading to further circulatory decline.